So this is the third lecture of 2025 by Harvey Friedman on invariant maximality. Please.
Yeah, thank you, Andres. So I'm thinking about how to present this stuff. Now, last time, and by the way, the notes for the last lecture are have been for many days, for several days on the downloadable lecture note page. Um, and and what I did last time, after giving you an update of positive results, uh, what I did is I gave a very general overview of of how the reversal works, uh, but it was not really detailed. Then I got into some details about the early sections. All right, so this time I'm going to do a deeper overview in which I actually present the headline from each of the sections and say something about how each one's accomplished. So we're going to talk about the whole reversal this today. Now, further lectures, I'm going to focus on one chapter at a time, and or maybe more than one, who knows. But I'm going to focus in on how I accomplish these headline results. I think any other way of presenting this is not going to work too well. Now, in the meantime, I have a running document on the downloadable manuscripts page, not the lecture note page, but the downloadable manuscripts page um, of the polished form of more and more, the polished form of more and more of the official chapter four, the official reversal in all of its glory. Right now, there's the polished form of sections 4.1 through 4.5. The number four refers to the chapter four, which is the reversal chapter. Uh, so you can see the gory detailed thing there, and then you can also see a copy of the notes that I give on each lecture. So we come at it from two different ways. Obviously, one is the actual gory stuff, and then there's the discussion about it. So we try to get. Uh, It's just a lot of it. This wouldn't be bad if it was just one chapter. The problem is one section. Sorry, the problem is there's just a lot of it. All right, so um, let's just review where we are. So the book is called Invariant Maximality: Finite Constructions in Games. Sometimes I fool around with the titles, and it has 6 chapters. The introduction has not been written. This has been written and is being revised to consolidate with the notation and terminology of the real stuff. The real stuff is chapters 3 through 6. The real stuff, double real stuff, is chapters 3 and 4. That's the real stuff, and the real stuff is chapters 3 through 6. Because this is the explicitly pi 0 1 things. All right. So this is being consolidated notation wise, hasn't really changed much. It does need some more polishing. And it's only for core mathematics. I only look at invariance in the reals, well, and also some other stuff, some other situations, but mostly in the reals. And I'm looking at invariance directly in piecewise linear in arbitrary comma and linear and semi-algebraic functions. And I'm interested in the direct invariance that they have. Now, the real subject is invariant maximality, and there, of course, we have invariance indirectly. Every widget has a every widget has a invariant maximal gadget. Every widget has an invariant maximal gadget. They're all the statements are like that. And and then I show a massive amount of equivalence of all of them. there are different variations and they're all equivalent. Then I pick one of them, my favorite one with cliques, and that's the one we're talking about that I reversed. So that reversing that reverses everything in invariant maximality. Everything in invariant maximality gets reversed when I reverse this in arbitrary dimensions. In arbitrary dimensions. Now there is this question of, what am I reversing on which dimension, which I know very little about. Okay, and this is the finite form, and this is a game theoretic aspects, which is interesting because you can get rid of quantifiers this way. All right. So today we're going to do a headline overview. Now, I should say that things are going very well with regard to larger cardinals. And the main reason that, and this in particular, the finite forms of yet larger cardinals seem to be very progressing. And that, I think, that is going to be a separate book. I'm not in this book, I'm only going to be dealing with SRP and below, only SRP, stationary Ramsey property, level of the large cardinals. All right. So we're discussing the reversal of this statement unchanged. Every order invariant graph has a invariant maximal clique. Okay. And in later in chapter 3, I attempt to analyze what you can use here. What functions, what order theory, this is an order theoretic function with parameters, with k plus one parameters. What order theoretic functions can you actually use here? That's called usability. And the idea is to analyze when I can use. And I'm doing well with that. That's a longer story. Let's not talk about too much here. I'm doing well with that project, figuring out what you can use. All right. So this recall the reversal looks like this is the reversal. They be the sections in chapter 4, and there are 11 of them. Okay. And the polished version of sections 4.1 through 4.5 is already on the downloadable manuscripts page. All right. So we're going to go through the entire reversal in terms of the headlines of each chapter and say a little bit about what's involved. And as I said, subsequent lectures will go into these headlines and show what's involved in more detail. I'll never be able to talk about all the details of any of these chapters. You'll have to I refer you to the actual manuscript because there's just too much detailed complication. But I can do what I can do, you know. All right. So, and now we've discussed this before, but let's restart it. So, the first substantive chapter, a section is 4.3, which is called atomic representation. And here we work in now the domain is always this until I get to it's really section 7, maybe the end of section 5, where we change the domain. We do use a more convenient domain, but first, in the very beginning, we stick with the domain that we're given for the statement that we're reversing, which is q minus 1, 1. In the rational interval, left closed minus 1, right open 1. And S is any invariant maximal clique given to us by the statement we're reversing in a rather complicated order invariant graph G, which is carefully designed to make this whole thing work. We're going to operate in dimension. We are operating in dimension. I'm sorry. We are operating in dimension K12, which is 12 stacks of 2s with a K on top. 12 stacks of twos with a K on top. I think that's a pretty big number usually. And we say J invariant because this is a function and we call it J. Now, the end of section 4.3, remember this is a headline overview, consists of three statements which represent all formulas expressible in three finite languages as an atomic formula and also negated atomic formula. This is a strong form of quantifier elimination because actually I'm eliminating both quantifiers and connectives. Now, in the subject of O minimality, one is eliminating quantifiers in favor, one is eliminating quantifiers, but one still has connectives. And that's very important. Whereas in set theory, you actually eliminate quantifiers and quantifiers and connectives in favor of purely atomic, in favor of X epsilon capital A, where A is the separation, right? In other words, for example, separation eliminates separation is an extremely strong example of atomic representation, right? Okay, so um, now, but there's a blow up here. Here, there's a blow up when you actually do this in the early section 4.3. You get a blow up. The number of parameters needed is totally out of control. Yes, you get atomic representation and a negated atomic representation, but the number of parameters is not controlled. In fact, the number of parameters is akin to, meaning maybe double of or something, akin to the number of formulas that we're treating. And remember, we're only treating finitely many formulas because we're doing this only for certain finite languages. And the parameters, fortunately, the whole point is the parameters that I use to accomplish this quantifier and connective elimination, atomic representation, the parameters I use are just among the indiscernibles. Actually, I don't use zero for this, but I could. That's a technical matter. Just all of them but zero I use as parameters. All right. Okay, so the finite languages I use, and here's the intended structure that they're used for. Uh, where S is the chosen invariant maximal Klieg S in the graph G. The first language, which is actually the really most important language, is L of K1, K1, K, where we have K1 variables and the complexity of all formulas is in most K1. And the K-ary relation, so this K indicates that we're having one relation symbol R that's K-ary. One formal relation symbol R that's K-ary that becomes this K-ary relation, namely the truncation out of S. Now remember, S is a K12 ary relation, right? So we want to just pick the first K. This always means this star notation I mentioned last time. This always means if I got a sequence that whose length is not is smaller than or at most K12, then I put star K12 means elongated so it has length K12. K12, if you remember, is the dimension I use also, which in fact is 12 stacks of twos with a K on top. All right. Now there's two other languages that are minor, two minor languages, a finite language that are also used. The first one is basically the same, except that K5 replaces K1. So complexity is K5. The arity of the relation symbol is K4. And uh, there are K5 variables. and we use the truncation of length K4 on S. However, this language, these two minor languages are used only for a very technical, brief period, and we only need the quantifier free part. And actually, there are other, yeah, we only need the quantifier free part. Yeah. Now, I should warn you in advance, I should say in advance that the only assignments in this language, in this structure that actually we use, the only assignments when we talk about atomic representation, uh, uh, involve any of the negative numbers and the all just the negative numbers and the wait a minute and the indiscernibles are not. Just a second. Uh, right, just the negative numbers. Yeah, the assignments for this for the assignments that we use are just going to be from the negative numbers, q minus 1, 0, open. The assignments that we use here are going to be involve negative numbers and the indiscernibles. And the indiscernibles, that is these numbers here, with 0 allowed. Yeah, yeah. But we don't have any quantifiers, and the same thing here. Actually, there's a technical restriction on this that I want the assignment to live in Q minus 1 comma a half. So I'm only going to use indiscernibles that are less than or equal to 1/2. Remember, half is a very big number in this system, right? When I go when I go incrementally like this, the number a half is in here somewhere, pretty big. All right, pretty far along is what I mean. So what do these representations say? And again, I talked about this before, but I want to do it more slowly, carefully. Um, Namely, if I have any formula with assignment X, and the quantifiers are all bounded by Q. The quantifiers are all bounded by Q, which is a number which is a negative number itself. And the assignments are all below Q. So the assignments are all below Q and Q is negative. Then I get a representation. And the representation involves Q, of course, and an X, of course. It's going to involve X and Q for sure, but there are no quantifiers or connectives here. There's just an outside negation sign here for one of the forms. And but however, notice that I'm using an ungodly number of indiscernibles when I do this atomic representation. All right. This is proved by a straightforward induction. It has to be done carefully. You know, you have to make sure you got the induction hypothesis going and you got the right setup. This is just proved by an induction on the complexity of phi. Phi I enumerates all the formulas that are all the formulas in this language, this first language. Okay. The second one and the third one are the same, except I only use certain assignments. The assignments now are allowed to be mentioned. The parameters, the positive part of the assignments exist, and are the indiscernibles, sorry, and then any negative numbers. Okay, and I'm indexing psi b. I'm indexing all the formulas that are relevant in the second language, and the third one, same thing. Now remember, there are no quantifiers there. I'm just eliminating connectives. And this is also done by straightforward induction. Straightforward induction. Uh, yeah, phi I enumerates all the formulas in this most important finite language. And psi b enumerates the formulas in this minor language, which and these are only quantifier free, and then rho do these. And this is just describing more formally what the assignments are for the second languages. For the second languages, I'm only going to use V and W. And there's a double max, MAXX here, which is just making sure that something is at least zero. So it's the uh, max with zero. It's the max with zero is what double max is. All right. These second languages are for technical purpose. All right. So now uh the next section is 4.4. Remember, we're in chapter 4. The next section is 4.4. It's called negative reduction. Here we push everything down into the negative part of Q minus 1, 1. This is required in order for us to get the stronger kind of indiscernibility. We need a stronger kind of indiscernibility here. The only indiscernibility we have from J invariance is that we can move indiscernibles with only negative parameters. We would like to be able to move any indiscernibles as long as we have parameters below the least indiscernible being moved, as in standard large cardinal combinatorics. We can't get that using the original indiscernibles because that would involve using positive parameters, and positive parameters are totally foreign to the J invariance that we have to work with. So in section 4.4, we actually obtain new numbers, some numbers R1, I don't know where I get this from. Didn't I start from 0? I'm sorry, I have to look at the manuscript, but not right now. I may have started from 1, in which case I have to change that to 2. I better look and see. All right, so uh, yeah, so we actually obtain an infinite sequence converging to 0 of negative numbers where uh, we actually have this stronger kind of indiscernibility. In other words, with these indiscernibilities, these R numbers, we have that if we move any two of them, we can use parameters below the minimum one moved. Okay, and that's stated uh, below here. But first we have uh, we also get, it's very important that we also get a new version of atomic representation. So here is the new atomic representation uh, that if we have any formula in this major finite language, the really serious one, and we have uh, an assignment below Rn, then the formula carved out is equivalent to an atomic formula where the parameters are also completely uncontrolled, but they're like what they were before. Parameters are the new indiscernibles. So we have new indiscernibles. Okay. Now, that's the atomic representation statement. Now we've got the indiscernibility I promised you. And this might look like a mess. Well, it is a mess, but it's just accurate, super accurate. It just says that if I have any, I'm using indices here, positive integer indices, and I'm using R of, uh, and and I'm just saying this just says that if I have a statement involving two sequences of indiscernibles that are order equivalent. I can use parameters below the any of all the indiscernibles. You can use parameters, and I'll have the same truth value, and I'll also be able to change the range of the quantifiers. This is this means the range of the quantifiers is being changed. Okay, this is the right kind of indiscernibility in this situation. So we're making progress here. We've got uh, infinitely many indiscernibles. They're of the strong kind that allow parameters less than all the ones moved. And we also have the same kind of atomic representation that we had before, uh, but we're allowed to do things less than any particular indiscernible. We can restrict the quantifiers that way. Okay, and we have to, yeah. Okay, so that's what happens with chapter four. Now, those other two minor finite languages are used in order to pull this off. Now, we won't talk about how I pull this off and how I use those finite languages here. That's a whole lecture. But this is what we have. Okay. All right. Now we want to attack this problem of having an uncontrolled number of parameters. There are other problems also. If you notice that this separation, that this atomic representation that we're talking about, is only for basically no parameters. In other words, there are no side parameters here. This is if x is length k1. This says that a k1 Airy relation can be written atomically with indiscernible parameters. A k1 Airy relation can be written atomically. Basically, is what it's saying. So we've got a lot of problems here. We've got a lot of we have an uncontrolled number of parameters, which is bad, and we also have because it's in real set there you have essentially no parameters or whatever, and in the representation. And the other bad thing is that this is only light-faced. This is only a light-faced representation. We're representing light-faced formulas. So, and the indiscernibility is very, very good. You can't complain, except that it's only for a finite language. And the whole point of this reversal is we have to get rid of all these problems. There are even other problems we've got. The domain is the rationals between -1 and 1, which is the most ill-founded imaginable thing, right? I mean, it's so far removed from having a well-founded, a well-ordered domain, which is something that we definitely want to have when we're trying to build a model of set theory. So we got a lot of things. So the tupling section is designed, the tupling section is all designed to handle the problem with having an uncontrolled number of parameters. We want to cut the number of parameters down. So actually, we cut the number of parameters down to 5. There's some overhead and technical issues involved in in the parameters. So yeah, I don't know how to do it with 4, and I don't know how to do it with 1 or 2, but I don't couldn't care less. It turns out not to be important. It turns out to have a fixed number of parameters, independent of all the other all the other integers in this statement. That's the whole point. All right. So, by the way, this thing here that we get uh, uh, is still light-faced. It's still light-faced. So it's still not that great, but it's a heck of a lot better than having an uncontrolled number of parameters. And the way we do this is we have to find a way to talk about to code arbitrary sequences or sequences that are big enough. Maybe, you know, actually we do better than this, but sequences of the length at least this. Yeah, we have to find a way to, well, actually, somewhat bigger. We have to find a way to code sequences of length, actually K12 minus 1. I mean, it's almost as big as you could imagine, big number, into one number. Well, that doesn't tell you why 5 are needed, but there's some infrastructure needed to help with this. All right. So we have this, we have this kind of light phase separation It's beginning to look like separation more and more, right? Like phase separation with this, which I just copied again, with this indiscernibility, which is quite good, except that it's for finite language. All right, now those two minor finite languages were used in order to pull this off, and so we never used them again. All right. So now we can consolidate what we're doing by talking about the structure M. So we have a structure M. The domain is just the negative numbers, and we're always using SK, that piece of S, uh, and uh, and the indiscernibles R1, R2, dot 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 that are unbounded in zero, that approach zero. So these have certain properties of a fairly conventional model theoretic nature. After straightforwardly shifting from the negative numbers to Q0 infinity, which is really, it's really mainly for convenience. I mean, it's a necessary. There's a thing called necessary convenience. So we obtain the following at the end of section 5. So here's the headline at the end of section 5. We get a structure M. This time on the non-negative rationals, with a relation R, which is K-ary. We don't have to worry about K-ary relations and henceforth. Um, we use K12. We use much bigger numbers because we had to do a lot of technical stuff. So it turns out that we had to use a lot of those, uh, use more arity, but now we cut back down in the way that I described. You know, R/K, if you remember, uh, picks out from the full R. Okay, and indiscernibles 1, 2, dot dot dot. Yeah, you know what? I think that now that it's not too important, I see that I counted from 1. Yeah. Where I screwed up here slightly. Just a second. Here it is. Okay. I don't think this is the most important thing we have to talk about, but here we are. All right. So index from 1. Okay. Tupling. We just did this. Okay. So here we are. There's a structure M, Q0 infinity, less than R, with the indiscernibles 1, 2. See how nice down there these indiscernibles are. 1, 2, 3, dot, 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 with the following property. Less than as usual ordering, that dense ordering. Not good that that's dense. R is the K is a K-ary relation on Q0 infinity. We have tupling. So we actually will be using the tupling again, not just the applications of tupling, but tupling will be used all the time in the future. So if I have any K minus 1 tuple, I can find a unique number bigger than its max, uh, such that R of Px, you see, so P codes X. And if X and Y have the same max and the same unique P, then X equals Y. So it's important that that not be stated stronger than I have. If they're the same max and the same P. See, so I'm coding uniquely things of the same max. Tuples of the same max are coded properly. But if they have different maxes, all bets are off. Okay, if max X is less than N, then this unique P is less than N. And that's only stated for positive integers. All my letters, N, M, R, S, T, are those letters are positive integers unless otherwise indicated. Okay, then we've got our representation or separation or whatever you want to say. Uh, we have that we discussed with five parameters, but it's only light phase, right? And then we have the indiscernible that we're talking about here. Okay, section 4.6 we're not going to talk about. It's a bookkeeping section, which involves keeping us honest that we actually really did have a graph G, pages of complicated definition, we actually have a graph G that we're really talking about, and we really have a maximal clique as arbitrarily picked, an invariant maximal clique. It's just a bookkeeping section. All right. Now, in section 4.7 is quite elaborate. I mean, it is quite detailed and long. And this representation, this light phase separation with 5 parameters gets upgraded, and it's only for this language. It gets upgraded substantially, page after page. I want to say more about this next time, all the way to getting to the full normal everyday logician's language L of K, which is just full predicate calculus with one K area relation and less than. I think I use equals also. I can't remember, but it's not important. And with infinitely many variables and formulas of arbitrary finite complexity, just normal language. And we still have indiscernibility, but only for the finite language. But we will have we will get the limited separation. And it has a slightly technical formulation. It says that even if I have parameters and I have LK definable with parameters, and here's the structure we really care about, that that I can represent it in the form set of Q, comma U semicolon M. The M is just bookkeeping because it tells you what the arity is. And Q is another bookkeeping that tells you where the limit is of the relation. And U is the real guts parameter, which is a 7-tuple. So now we have 7-tuple representation for arbitrary first order, limited, bounded, quantifiers bounded, limited, and with parameters, with any parameters. Okay, this is a huge improvement. So this really is a very, very good shape. Now, you might say, well, what the heck is this? Actually, we're not going to talk about it today, but this is something technical. This is something, it doesn't make any difference what it is. The only thing that you need, the only thing that's important about this is that this is a uniform representation, that this itself is LK definable, limited LK definable. You see, you don't really, it's not too important what's in here. I mean, I actually make it go out of my way to make it fairly clean, but it's not, just to establish this, but it's not important. Okay, so here's the summary of where we are. We have this structure, same structure, except I now have got proved a lot more properties of it, more properties, not change the structure. The usual ordering, and these are going to act as indiscernibles. We're going to have tupling. We're going to have the indiscernibles that we really want. They're just fine, except it's only for a finite language, which is something that we have to address. We eventually address. And we have the limited separation in a really good form, where it's not important what this is. It's just a uniform thing with 7 parameters. We're representing definable M-area relations uniformly with 7 parameters. Exact nature, as I said, is not important. We'll have to go into section 4.7 in more detail, probably in the next lecture. Okay, the structure M has some very good forms of tupling and limited separation, pretty good indiscernibles. Would be very good if only the indiscernibles weren't limited to finite language. But the big drawback with M for making further progress is that its domain is horrible. It's a dense linear ordering, nothing even close to being well ordered or internally well ordered. Section 4.8 is devoted to defining a suitable well-ordered system over M. We don't create any well-ordered system of points in M. We don't do that. Rather, we work with a robust definition notion of M-definable pre-well ordering. So we look at the M-definable. Now, M-definable, you have to be a little bit careful. It means there has to be bounded quantifiers. But M-definable pre-well ordering whose field is upper bounded in M. So these are these pre-well orderings on initial segments, so to speak, that are definable. And of course, they're well ordered and definable only in the sense of M. Now here's where we really need the limited separation we proved, the wonderful limited separation. We need that and the indiscernibility. You need both in order to prove the comparability of well orderings. In other words, the appropriately definable comparability of appropriately definable well orderings. It's not actually well orderings, it's pre-well orderings. It turns out you can't factor. You don't want to factor. I mean, excuse me, you don't want to pick representations. You really need pre-well orders. Okay, so let's see. Pre. Yeah, I got all the pre's. Okay. Now, this setup here, defining the M definable pre-well orders and the comparability and all that, and they're all comparable and blah blah blah, and they all do what they're supposed to do. They're high up, they're like a proper class and all that stuff. That's all preliminary to section 4.9, the next section, where we create an internally well-founded structure. Maybe I should say internally well-ordered. That's actually what I have. The structure X equals D less than D pair set epsilon U1, U2, U2. Okay. D is going to be the set of equivalence classes of the M definable pre-well orders under M definable isomorphism uh, from section 4.8. And note that this is a second order structure. So pair is going to be a ternary relation on D, univalent and all that. 1, 1. Yeah, univalent. And this is going to be a collection of subsets of D. Collection of subsets of D. This is the epsilon relation. Obviously, not all subsets. We're just everything's countable here. The whole subject is countable. U1, U2. This is uh, a preferred. This is a preferred collection of the sets of yeah. These are preferred collections of the sets that grow. They're bigger. The sets are there's a bound to all the ones in here. There's another bound to associated with C with a constant C1, a bound associated with all the sets here. U1 contained in U2 contained in dot dot dot, and there's more sets each time, and they're higher. And these are particular elements of D that are going to be our new indiscernibles. These are going to be our indiscernibles. Remember, our indiscernibles used to be 1, 2, 3, 4, dot 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 when we were in the rationals, but now we're in this abstract space where we took uh, D was the collection of equivalence classes, right? Of pre-well orders. All right. D is a set of equivalence classes of pre-well orders, M-definable pre-well orders under M-definable isomorphism, section 4.8. Yeah. Note that X is a second order structure. So we go to this convenient second order structure. And so the headline of section 4.9 goes like this. I'll just, it's, some details here. Less than D is what I said, least element 0 plus 1 is successor. Set is a family of subsets. These indiscernibles grow, and they're unbounded in D. And these form a chain of subsets of S set, and the union of this chain is all of set. Every element of set lies in UN. Yeah, union is the same. And every set UN is a subset of some 0D, D less than Cn. See, that's how the N comes in. Pair is the ternary relation, which is the graph of a bijection, where the bijection preserves the right kind of ordering on pairs. This is max first and then lex, max lex. All right, and some other properties that it's dominating. And oh, and f of zero, yeah, these are things that are derived from the natural way to do this, and pair maps each 0 Cn squared on 1 onto Cn. So we have a really good pairing function. We have we also now, this is very important, we have internal well ordering. Every non-empty subset element of set has a less than D element. We have internal well ordering, and we also have this soup, which might be derivable if I have enough stuff, but I think it's better just to state it, that every element of set has a less than D least strict upper bound. So we have soups. Remember, this is only a second order structure. This is not a set structure. In other words, the domain is, think of the domain as ordinals, and the sets are bounded subsets, bounded sets of ordinals. Then we have limited separation. Uh, uh, yeah, we have limited separation for the entire language. These are bookkeeping numbers. X is the X is the structure we're talking about. So we're talking about the language of the structure we're talking about. And we have this. This is the separation we want. That we can take. Uh, we can use parameters from UN minus one and parameters below D and bound the first order variables to D and the second order variables to UN minus one and get something inside U of N. This is important to have. Okay. And then we have the indiscernibility. But the indiscernibility, again, is exactly what we want and really hasn't changed. That you can move indiscernibles of the same order type, sequence of the same order type, as long as you have parameters below. And this is all sort of refurbished a bit for the second order language with no surprises. Uh, However, we still are only doing this for a finite language. We're still only doing this for a finite language. And we can now don't have to get involved in the technical language we were talking about before. We could just talk this way. Complexity at most K. Okay. So we still have this, which is annoying because we've gotten rid of K before everywhere else because pretty much. I mean, we do have. Do you talk about K-airiness? K-airiness is still all right, but yeah, actually, we have gotten rid of the relation R, which is K-airy. Yeah, so we've gotten rid of all mention of K except there, which is very nice. That wasn't obvious you could do that, but you can. Now let's get rid of this problem with K. Now we step back and say, what have we done? We have shown, let's reflect on it. We have shown that for every K, there is a structure X like this with these properties. That's what the whole point is if they're up to now. But now we can apply compactness for first order predicate calculus and get this removed because we can do this for each K. For each K, we have the consistency. Something is consistent, right? For each K, and then if K grows, we have even stronger property, right? We can just go to the limit just simply by ordinary compactness for predicate calculus. So reflecting on what we've done, we've now released, because remember we did this for any sufficient large K, we now release K entirely, and now we get a statement like this. The same statement, uh, the same statement, but now the K is missing because now we have the indiscernibility now for all formulas. We have just X indiscernibles for all formulas in this second order structure. Now we have a fairly standard situation for contemporary math logic. In the remainder of section 410, remember there's only 11 sections, so we're doing pretty good, um, uh, is devoted to building uh, a structure W which is basically is just like the structure that we just stated, except it's an inner model of L. In other words, this is basically Gödel's monograph of Gödel's L. We want to consolidate into L. We need this in order to get more, to be able to use the indiscernibilities properly. We have to go to an inner model. We can't use the indiscernibilities to get partition properties like SRP internally without having a definable well ordering of the universe, a good one that we can use. So $I is our well ordering of the universe. It maps uh, the old UI 1 1 onto 1 1 into, we only do this into first, into the ordinals, so to speak. So we get a structure W, this time without these U's, still with the C's, but these are replacing the U's. These are uh, defining our well orders of ever growing pieces of the sets. Okay, and so all its scoring. Oh, and extensionality is not a problem. We put extensionality in here, which is well worth it. I think we did that maybe before, but I don't remember. So we have the indiscernibles go up. Uh, the dollar signs do what they're supposed to. We have a binary operation as before with the same properties. We have the well ordering and supremum as before. We have limited separation, which is unchanged, except that dollar signs are used instead of capital U in the formulation. It's really the places where dollar sign is not the identity. That's the old UIs. Dollar I is not the identity. The set of places where dollar I is total, but where it's doing something serious is exactly the old UIs. All right, so we have the indiscernibles in the obvious way. And now this gets upgraded slightly, but it's important. We upgrade it because we actually have surjectivity. See, these dollar signs, these dollar I's go into the ordinals. They go from sets into the ordinals, 1 1. But they're only into. But it's important to have them onto. This is important when we go on, if we want to smoothly convert to a model of set theory. So this W is really the same as the previous W, except that we just have this surjectivity of the dollar signs. Okay. And now we go to the epsilon relation. The epsilon relation is given by D is a member of E if and only if D is in the inverse of dollar sign N at E. You see, E codes a set. So D epsilon E means D is a member of the set coded by E. And this doesn't make any sense unless we have surjectivity. This isn't good unless we have surjectivity. That's why we want the surjectivity. Then we show, remember, the section 11 is the last section we need to talk about, and I'm almost done. I'm just going to go over a few minutes. I started a few minutes late. So we look at the structure 0 to Cn, the nth indiscernible in this system, with the nth epsilon relation, and we show that that is a model of ZFC with some trouble. I mean, we have to go through each axiom and show that everything is okay. So we get models of ZFC. Well, that's something. All right, now the ZFC model going from the n plus third indiscernible with EP n plus 3 is referred to, let's call this capital Y. Okay. Y satisfies that ord of Cn plus 1 is purely n plus 1 subtle. Okay, first of all, what the heck am I talking about? Purely subtle is just a technical weakening of subtle cardinal. which is cofinal in the SRP hierarchy. Okay, so that's nothing. Cn plus one is just a point in the master structure that we're doing, which is capital X, right? Well, I call it capital W now, right? Because well ordered and all that. That's not the same as what an ordinal might be in these models we've constructed under EP. EP is not the same as less than. EP is more complicated. So the notion of ordinal of a point has to be defined carefully, and the obvious proofs have to be given. It's really the only thing that's isomorphic. See, we have two kinds of ordinals going on. The ones in this master structure W, and the ordinals that come out of when we make these models of set theory. When we make these models of set theory, we have ordinals there. These are not the same thing. We have to argue, define what we mean by one correspondence between the two. So the ordinal corresponding to Cn plus one is a large cardinal of the appropriate kind in Y. So we obtain a model of ZFC plus their existent ordinal with the NSRP for any standard N, because purely purely N plus one subtle cardinals have an NSRP cardinal below them. See, I told you that was cofinal. For any standard N, hence we're done. Con SRP. That completes the reversal. Andreas, I'm done.